All right, CUET fighters, listen up. We're about to tackle a topic that literally separates the top rankers from everyone else, the rate law. You know the pressure's on, and every single mark is crucial. Today, we are going to make sure you're the one climbing the ranks, not slipping down. Let's kick things off with a question that trips up almost everybody. So you see a question like this in the exam. Your eyes, hey everyone, and welcome. You know how chemistry textbooks just love those perfect standard conditions, right? Well, today we're going to break out of that ideal little world and get our hands on a tool that handles chemistry in real, messy, changing environments. And that tool is the Nernst equation. So let's dive right in. I mean, that's the real question, isn't it? Textbooks have to simplify things with standard conditions. But think about it. In a real lab or a car battery or even inside our own bodies, conditions are always changing. So how on earth do we predict what's going to happen then? Well, that's the big problem we're here to solve today. So here's our game plan. First, we'll talk about why those standard conditions just don't cut it. Then we'll introduce the Nernst equation itself and really break it down. After that, we'll focus on the single most important factor, concentration. We'll even connect it all to Gibbs energy and equilibrium. And, of course, we'll wrap up with some crucial tips to help you ace your exam. All right, first things first, we have to understand the limits of those perfect, squeaky clean lab scenarios you read about. You know those standard electrode potentials you look up in the back of your textbook? Well, they're measured under super specific, totally fixed conditions. But real chemistry is messy. Concentrations are constantly shifting and changing. We absolutely need a way to calculate potential in these dynamic, real-world situations. And that, my friends, is where our hero of the day comes in, the Nernst equation. It's literally the bridge that connects the ideal world of the textbook to the actual reality of the lab. Okay, so formally speaking, the Nernst equation gives us a mathematical way to figure out how the potential of an electrode, its tendency to either gain or lose electrons, is affected by the concentration of everything involved in the reaction. It is the key to making accurate predictions when things aren't standard. Now, you're going to see this equation in two main flavors. On the left, you've got the general version. It works at any temperature, which is cool. But on the right, that's your go-to. That's the one you'll be using pretty much all the time, especially for exams. It's simplified for room temperature, 298 Kelvin, and it uses log base 10, which makes the math way, way easier. So let's take this thing apart, piece by piece. First up, E. This is our target. This is the whole point. It's the actual potential of the cell you're looking at under the specific real-world concentrations you're dealing with. Next, we have E0, which we say as E0. Think of this as your baseline. It's that standard potential you look up in a data table, the one measured under those perfect, ideal conditions. It's our fixed starting point. Then there's N. This one's pretty straightforward, but it is absolutely critical to get it right. It's simply the number of moles of electrons that are getting passed around in the balanced reaction. Make a mistake here, and the whole calculation is thrown off. And finally, we have Q, the reaction quotient. Now this is where the magic happens. Q is what brings reality crashing into the equation. It's the ratio of your product concentrations to your reactant concentrations at that very moment. Okay, now we get to the real heart of it. The whole reason this equation is so incredibly powerful. It all boils down to one thing: concentration. Seriously, if you remember only one single thing from this entire explainer, make it this. Say it with me. Concentration controls potential. By changing how much stuff you have in your solution, you are directly controlling the voltage of that cell. It's amazing. So, how does that actually work? Well, it's a pretty direct relationship. If you increase the concentration of the thing that wants to gain electrons, that's the oxidized species, you increase the chemical push for the reaction to go forward. It's kind of like Le Chatelier principle. You're adding more on one side, so the system tries to balance it out, which in this case means the reduction potential goes up. You know, the Nernst equation isn't just some isolated tool for calculations. No way. It's deeply woven into the very fabric of chemistry, connecting to huge ideas, like whether a reaction will even happen on its own. See, there's a direct, beautiful link between cell potential and Gibbs Free Energy. This simple equation right here connects our standard potential, E0, to delta G0, which is really the ultimate scorecard for a reaction's spontaneity, its natural desire to just happen. And that brings us to this incredibly useful rule of thumb. Because of that little negative sign in the formula, a positive standard cell potential will always give you a negative Gibbs free energy. And what does a negative delta G mean? It means the reaction is spontaneous. It'll go all by itself. What a great shortcut, right? So what happens when a reaction finally runs its course and hits equilibrium? Well, think of a battery dying. The juice is gone. The net push, the driving force, is zero. So the cell potential, E, becomes zero. And at that exact same moment, our reaction quotient, Q, is now equal to the equilibrium constant, K. All right, let's bring this all home. We've gone through the theory, which is great, but now let's laser focus on the absolute must-know points so you can walk into your exam feeling confident. Okay, here's your final checklist. First, unless they tell you otherwise, always use that simplified equation with the 0.0591 constant and log base 10. Next, and this is a classic exam trap, remember that potential depends on concentration, not just the total amount of stuff you have. And finally, burn these last two into your brain. At equilibrium, the cell potential E is zero, and a positive E naught means a spontaneous reaction. Got it? So, I want to leave you with this final thought. The Nernst equation isn't just about plugging in numbers to get an answer. It's a tool for control. It literally gives you the power to manipulate a reaction. So knowing that you're in the driver's seat, how could you change the conditions to build a better battery or make a cell that delivers more voltage just by tweaking the concentrations? That right there is where the real chemistry begins.